I like how Keynote links my email address in case I want to email myself. Okay, so my name's Perrin. I'm going to give you a hi. I'm going to give you a breezy introduction to profiling today. So you've probably all seen this quote before. It's the premature optimization is the root of all evil, famous quote. I want to draw your attention to the second part of it today. A good programmer will not be lulled into complacency by such reasoning. He'll be wise to look carefully at the critical code, but only after that code has been identified. So in other words, use a profiler. This is another good one from Rob Pike. Bottlenecks occur in surprising places, so don't try to second guess and put in a speed hack until you have proven that's where the bottleneck is. And it sounds like Rob is giving you permission to hack the hell out of it once you do find the bottleneck. So profiler, basically once you reach the limit of using print statements and maybe running some benchmarks and time it, and you're still not quite sure where all the time is going, that's when you need to call in a profiler. What you're going to find out from that is the function execution time. The execution time for every function in your program. You can use profilers for memory and other things, but I'm not going to get into those today. And you also can profile on a line level, which I'll say a little more about later on here. And we're going to look at real or wall clock time. It is possible to measure CPU time, but it's not so useful for profiling usually. In modern programming, most of the stuff that is slow tends to be like database queries or network I/O, and that stuff won't show up in CPU time. So that's why we use real time for profiling. We're going to get inclusive and exclusive time for all of our functions. The difference between these is inclusive time is all the time that the program spent inside a function plus inside every function called by that function. And exclusive time is all the time spent just inside the code in that function, not counting any subroutines it called. We're also going to get the number of calls for each function, and that'll be primitive and recursive. So what is a primitive function call? It's one that is not recursive. Okay, so the common profiler to use for Python is cprofile. And what this does is generate some profile data, which you can read in the shell with the pstats, or you can use a GUI tool. And I'll show you examples of both of those. You're going to get a pretty big speed penalty by running the profiler. You should expect probably at least 30%. So typically this isn't something you do in production, or you would do it very carefully if you do. This is how you invoke cprofile. If you have a command line script, you can just run it like this. You can see the -o option I'm using there is telling it where to write the file, which file to write the output to. You can also call it from inside your program. Here I'm saying run this function and write the output to this file name. And if you need even more flexibility than that, you can just load up a profile object, tell it, start profiling, do your work, and then tell it to stop. Once you've got that written to a file, then you can load it up in pstats. And so what I'm showing you here is we're loading up our profile data. You can also, if you have data from a previous run that you want to fold in there, you can add that in too. I'm calling stripders mostly because it helps it fit on a slide. What that does is remove the path info from the function names. And you'll see on the next slide what I mean by that. And I'm going to sort the stats by cumulative time. So unfortunately, everybody uses different names for these keys. Cumulative time in pstats is inclusive time. And then I'm going to ask for the top 20 ordered by inclusive time. So this is what you get for your trouble. So it's telling me the number of function calls and primitive calls, and the total time it took. Incidentally, this used to say in CPU seconds, which was wrong, so that's been removed from more recent versions of pstats. And what you have here is a list of the functions. With each one, we have the number of calls. We have the exclusive time, which here they call total time. We have the exclusive time for each call. And then we have the inclusive time and the inclusive time for each call. And then the file name, which is what I stripped down. That would have been a full path. And the actual function and the specific line number. So this is great. You may notice that the order it's in is just by time. There's no information here about who is calling who. And usually when you're trying to make sense of one of these profiles, one of the first things you want to find out is which function called which. So to do that, you need the print callees and print callers functions. Okay, so print callees, it's pretty simple. You pass in the name of the function that you want the callees for, and then it tells you, full clean was called by, this, this, and this. And you can see here I've actually got multiple full clean functions in this code that I'm profiling, and I didn't specify which one, so I'm getting them both. If you just want to get one of these, you have to be a little more precise. You can include like 260 full clean. It's just doing a string match, so it's a pretty dumb match. And you can do the same to get the callers. So, that's great, but if that looks like a lot of typing, you can go a more point-and-clicky way and load up KCashGrind. This is actually, it's a GUI that was made for the KDE project for going through profiles from C programs, but we can adapt it for our use. You basically just take your profile output, you run it through PyProf to call tree, which is easy to get. If you have a Mac, you may find it easier to install QCashGrind, actually. It doesn't have all the extra KDE tie-ins. And so this is what QCashGrind looks like, looking at the same profile. So you can see I've got a few different things here. We've got a nice sort of sortable table of data on the left there. The thing scrolling off the side is the location, the actual file and line number. And then I've got a couple panes where we can do different things. Not all of this stuff actually works for Python code. Like machine code doesn't work. But you can use the callers and the callees stuff. And so, this is great for if you just want to step through pretty quickly. You can also get this crazy map. This is the callee map. Now this is from like a pretty top level, but even so, I find this pretty useless, but it's impressive. You do get a little more information when you roll over things. So another option that you have is RunSnakeRun. This is a Python program using WX Windows. And this does something pretty similar. It gives you a table you can sort, and it does a square map of the call tree. So let me show you what that looks like. This is actually it's a pretty nice way to look through the profile with the data table. The actual map is kind of crazy and probably not that helpful. I mean, you might be able to pick out like, wow, I'm spending a bunch of time in like one particular thing, but like this code, I couldn't tell you where to start with that. It does get a little better when you get deeper in. So like here's maybe like 5 levels down in the call stack. So it's starting to be comprehensible, but still, I would say basically you're going to be using this to look through the data table and maybe get this nice output of callees on the right. Okay, so once you have your results, what do you do with them? I've got a couple approaches I tend to use. The bottom-up approach is where you sort things by exclusive time, and then you start with a sub that's got a large exclusive time and sort of climb up the graph looking for something that you can actually change. The stuff that's got large exclusive time is often things that you can't directly work on, like maybe MySQL execute or something like that. So you end up sort of walking up to find where can you actually make a change. my example of this is, you see, wow, we're really calling deep copy a lot. Why are we calling that so much? And you look up to see, where that's coming from. The downside of doing it this way is that you might miss some higher level fixes, structural changes. So in order to catch those, I would also do a top-down approach. And this is basically taking the inclusive time, starting with something with a large inclusive time. That's probably going to be like an entry point in your program. And you walk down there looking down the call stack for something that you can actually change to improve things. So my example of that is you see, wow, this validate method really takes a lot of time. What's it calling that takes so long? Maybe there's some work we're doing here that we don't have to do. And here you're looking more for structural changes. So like I said, there is a line profiler. I wouldn't really recommend using it. It does work. People like it. But my feeling is that results at that level are hard to use. Typically, you're not going to get a big speed up from a line level change. And I think that usually the reason people reach for the line profiler is because their functions are too big. They have like a 600 line method, and C profile isn't really telling them where the problem is. So you're probably better off refactoring and splitting up your methods if you get to this level. Word about good technique for profiling. You typically want to start by creating some kind of a benchmark that you can run. That lets you know when you're winning. You can say, well, I found this thing and I made this change to it and I got like a 10% speed up for that change, or it didn't seem to matter, or whatever. Usually you measure this by looking at how many iterations per second you can get, or like, it takes me 2 minutes to do 500 iterations or something like that. So then you can compare between runs and see whether you're going in the right direction. And then a few words about what usually helps. One big thing is removing unnecessary work. So you might be using a top-down approach and discover, we're loading this config data. We only use it on like a quarter of our requests. So maybe you can put in some conditional code and only load that when you need it. So you're making a swap there. You're adding more complexity to your code in order to get some speed. You might also discover at this point, that maybe you did like a little brute force method on something in order to get the code working, and now the profiler shows you like this has become a problem as your data has grown or something like that. So you might look for algorithm changes. A lot of times I/O is the problem, so batching your disk or network operations can help a lot. And of course, all the usual database stuff. Profiling is definitely not the only way to find out what's slow in your database, but it is sometimes a nice way to go because you're coming from the direction of the code you want to speed up rather than just what are all the slow queries in the last 24 hours. And then of course there's the final thing, which a lot of people reach for caching first, and I used to do that too, but I've had it bite me so many times that now it's a little more of a last resort. The thing about caching is that you can really build up a lot of code complexity very quickly. Before long, you end up having a lot of invalidation calls all over your code to clear caches. You have to keep track of dependencies between things. If I clear this cache, then I've got to clear that cache, etc. And the other big problem with it is that business customers tend to actually care about data freshness a lot. So, if somebody comes to you and says, I changed the price on this product, when's that going to show up on the website? And you're like, well, we've got the database cache and the object level cache and the page fragment cache, so it'll be about 2 hours. So, it won't make you popular. So, wow, I tore through these slides. So I actually can probably show you a little bit of what these things look like. Here's QCashGrind, And you can see it's got like, oh, it's not showing? Damn it. Let's see. All right, we're not going to look at QCashGrind. I will pull it back up, though. You can see everybody has a different name for these things, right? Like QCashGrind has inclusive, and they have self for exclusive. If you look in RunSnakeRun, they use some of the pstats names. They use cumulative, but they have local instead of total time, or as I call it, exclusive time. So you just kind of have to translate. So since we have time, questions?
I was actually dealing with blogging production where we have this thinking process from the server to the iPad, and something changed and it's really slow. And so I used the profiler to figure out where everything was, where all the time was being spent.
Mm-hmm.
And it unfortunately didn't reveal anything, because what I had to do is I had what I wanted. One of the questions, sorry, is do you know of anything that will do the crawl, like the git commit tree and measure the times for every
You mean like try to find out what changed between the slow version and the fast version?
Like a bisect that's automated with profile.
No, you're going to have to do that the painful way. I don't know. Probably somebody could like rig something with a VM and BuildBot or something, but I don't know of anything already created to do that. The question is basically.
Doesn't get bisect do that? I think you still have to manually run.
Yeah.
It's just I don't think it knows what particular function I want on a profile. The best way is just have a injection all the time from profile. So when you take a video, find all the time, go back and check.
Yeah, I mean, you could certainly do. The level you're talking about is not necessarily a profiling level. It's more of like a benchmark level. Like you want to know when did things get slow, and you want to sort of step back until you find where things were fast. You don't really need a profiler for that. You need more just like some basic timing output maybe from your test suite. So yeah, but that's. Yeah.
Basically trying to do sort of this, like the same way that you write a test suite, and then for every commit you result you can run the test,
Mm-hmm.
write a benchmark, and then as you commit, you run the benchmark, and you kind of track the performance. Is that called VBench? So I know pandas is that well for this, but I don't know anything else does, but it does.
Mm-hmm. Everybody catch that? VBench? Yeah, good question, actually. Yeah, so the question is, if you want to exclude certain things from C profile, so that you want to focus on specific code, you can actually, it's just called filter, and basically it's like, it's another dumb string match, but it's really easy to use, and I've done that before when like, you're not interested in like, what your ORM library is doing, because you're not going to optimize at that level. So you really just want to see, what's going on in my code. So filter can do that for you.
Is that post?
It is after the profiling, yeah. Yeah, so you will still pay the performance price for that, but at least it'll help you analyze it. Yeah. Yeah.
These profiles will alert you if I'm like flooded and actually
No, it's at a Python level. It's not going to analyze your C code.
Can we go back to the role profile data?
Sure.
Yeah, so it says blah 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 functions calls in 84 seconds. How does this number relate to what a SQL?
Well, that is just the total runtime, like same thing you get if you ran. The question is about the 84 seconds at the top.
I mean, this number is smaller than what a SQL like working module and
Right. So you're asking where's that missing like 0.2?
yeah, and if I like get sum together all these numbers and the number that is significantly larger than that. So I'm just trying to understand where that top number comes from and how it relates to the all the times that it's below.
Yeah. So the question is about how do you explain the discrepancy between the seconds at the top and the seconds for like the most expensive function that should include everything? I guess the real answer is I don't know exactly, but some of this is just like inefficiencies in measurement. C profile is pretty good, but there's only so precise that it can get with typical clock. But there may be an actual answer to that in terms of what's included or excluded in each one. Maybe it's making an effort to exclude the time taken by the profiler itself or something like that. But the real answer is I don't know. Anybody else?
So this is great. I actually saw a lot of things that I think are very useful for doing profiling on the actual execution time. Have you worked with any tools in the Python tool chain that actually help you to diagnose memory profiling issues?
So this question is about memory profiling. I actually haven't personally had to do that. I know that Dowser is one that a lot of people recommend, and there's a couple others that come up a lot. If you were to look at, you can easily Google this stuff, but there's also some discussion about this in the Performance Python book from O'Reilly. But I can't really recommend one specifically because I haven't had to do that. Anyone else?
What was the name of the first
So there is KCashGrind or QCashGrind. That's this one. And the other one is RunSnakeRun. Both of these are pretty simple to get going on a Linux system. QCashGrind is relatively easy on a Mac. RunSnakeRun took a little fussing, but not too bad. Anybody else? Yeah. Yeah. Well, okay. So if it's not clear what's being shown here, let me go to the next one because it's a little better. What you're getting is the size of these boxes relates to the amount of time spent inside each function, and it's trying to show you also the difference between the inclusive and exclusive time. So you'll see that some of these top ones, there's really not very much space at all that's not taken up with the interior boxes, meaning like there's not much exclusive time here. It's really just inclusive time, but the inclusive time is big. So what you can get out of this is like, say, oh look, method query on MySQL is actually takes up a lot of exclusive time. Not too surprising because that's where you're doing a lot of I/O wait. Okay, that's it. Thanks, everyone.